Hello everyone, welcome to the class once again. I hope you're all doing good and you're in the best of your health. So till now we have already studied about the satellites and planetary motion and have studied about what is the time period, what is the velocity of a satellite. In the last class I was telling you that a satellite is moving in an elliptical orbit. Based upon this elliptical orbit, Newton and Kepler actually already gave that the planets are revolving in elliptical orbits. Kepler gave us some gravitational laws which are actually controlling this motion of all the planets, and we'll be studying today Kepler's law. Kepler's law, let me begin the class with understanding the planetary motion and what Kepler said about planetary motion, Kepler's law. Now Kepler said that he gave us three laws which actually control the motion of the planets around the sun. Now the first law is, it is a law of orbit that every planet is revolving in an elliptical orbit with sun at the focus. You see here in the last class I was telling you, if this is the sun and if sun is present at the focus of one of the elliptical orbits, the planets will be revolving all around here. This is the orbit of the planet, this is an elliptical orbit. This is what we have studied in the previous class. So Kepler said that every planet is moving in an elliptical orbit and these orbits are bounded orbits. Every planet revolves in an elliptical orbit. So you can take down this statement that I am saying. Every planet moves around the sun in an elliptical orbit and these orbits are bounded orbits. So elliptical orbit, 1 point. And these orbits are bounded orbits. This is the first one, second one. When I say bounded orbits, what do I mean by these bounded orbits? This means that these orbits are stable orbits. The net energy of the planets moving in this orbit will be negative. It will be lower than zero. In that case, when a body is having negative potential energy, that means negative total energy, that means the body is stable and it will be continuously revolving in this elliptical orbit. If the energy was positive, then the planet would be in such a state that it could leave the orbit and could fly off. But we generally don't find this situation. The planets remain in this elliptical orbits and they move here. Now, sun is at the focus. Sun is at the focus and I'm drawing two focus here. One focus here also I'm drawing. So two focus we have. These are the foci of an ellipse. Now you see here planet is revolving. One time it will be at the nearest point with respect to sun. This is the planet which is revolving. And one time it will be further away from the sun. Planet at the second position. You see your sun is here. This point will be nearest to sun and this point will be further away from the sun. What is this position called? In the case of satellite, we have given you apogee and perigee as the farthest and nearest position respectively. Here in this case, we have the nearest point is known as perihelion. The nearest point is known as perihelion and the farthest point is known as aphelion. Aphelion is the name of the farthest point. Now, how can you remember this? It's very easy. As I told you in the last class, do remember FANP, fan and P. This is the shortcut to remember F farthest, aphelion, N nearest, that is perihelion. Do remember this. Farthest, aphelion, nearest, perihelion. That is what I have given you. Nearest, perihelion and farthest is aphelion. That is what I have written here. That is easily you can understand with the shortcut way to remember fan P. Next thing, first law, they are moving in an elliptical orbit. Then already I have told you because the velocity is not as equated by L root gm by a, it is not the speed. And now one more thing, if the speed you take at 2 points, let me mark here speed as v1 and here the speed as v2, the planet speed, when it is nearer, it will be revolving with a higher speed compared to the speed when it will be further away from the sun. When it is further away from the sun, then its speed will be lower. So I am writing here v1 will be greater than v2. And we have seen this relation. When we conserve the angular momentum, in that case we realize that the speed is more than it is nearer to the sun, and when it goes further away from the sun, the speed will be lesser. That is what I have written. V1 will be greater than V2. Next part, the second law of Kepler. The second law states that it's the law of area. Second law, law of area. Very simple law it is, law of area. Now this law says that the line joining to the planet and the sun sweeps equal area in equal interval of time. I am writing here the law, the line joining sun and the planet, the line joining sun and planet sweeps equal area in equal interval of time. Sun and planet sweeps equal area in equal interval of time. Hope that's easily you can get that in equal interval of time. This is what is the second law says, that sweeps equal area in equal interval of time. And it's quite easy to understand with this statement what I mean to say with the second law. Suppose if I draw here again the position of the planet keeping the sun at one of the focus. This is the sun, and see, I'm going to draw the elliptical orbit in this way. This is the elliptical orbit. This is what we can observe. Now you see, when planet is revolving, let's say planet is here. At some time it is at this position. If I join this line with sun, if I join the line connecting the sun and the planet in this way, after some small time delta t, this planet will reach at this particular location, let's say making an angle d theta, let's say. In time dt, it moved from here to here and sweeping an area given by the shaded portion. This is what has been given in time dt. It has moved from this position to this position, sweeping an area. Now in the same time dt, if I take planet's another location, suppose the planet was here, let's say the planet is here, and the same time dt it reached here. So if I connect these two positions, see what I'm going to obtain. I'm going to obtain the same time dt, this time it has covered this much distance, and the area that it has swept, that will be given as this. This will be the area that I am showing you with the shaded region. This will be the area. In the same time dt, the first case planet has moved from this position to this position. The second case it has moved from this position to this position. Kepler's second law says that in same time interval, the line joining sun and the planet sweeps equal area in equal interval of time. That is, rate of sweeping of area is constant. Now that means if I mark this area as delta A, this area will be also given as delta A. This you should be very well aware of. Both the areas will be equal, or let me write the law, dA by dt is constant. The same thing can be proved also. We can treat this as a triangle. We can show that the same thing can be proved also, but that proof is not required in our syllabus, that is not in our curriculum. So let's not get into the detail of the proof of this law of area, and let's directly switch to the third law. And before that, let me tell you about this law of area once again. Remember, you have to check this line. In some time dt has moved here, this line has moved here. The area that it has swept, this will be the area. This has to remain constant. If you take a large time interval, let's say the time of, let's say 1 month. In 1 month, the planet has moved from here to here. And the area will be swept will be this much area that you can see. And in the second motion, let's say planet has moved from here to here in the next 1 month. The area swept will be the same. And the same thing can be shown also, it can be proved also mathematically, but that is not required, so we're not going into detail of that. You should know that this only, that the line joining will be sweeping equal area and equal interval of time. Let's go ahead after learning the second law. The third law is quite simple. And third law is based upon that planet is moving in an elliptical orbit. First of all, I was talking about this elliptical orbit. This is the first law. I told you that every planet is moving in an elliptical orbit. Now I have shown you two axes. In the last class I told you this is the minor axis, this is the major axis. Let me give you the length of this major axis as 2a, and let me give you the length of this minor axis as 2b. If E is the eccentricity of this elliptical orbit, what I'm going to mark here, let's say E is the eccentricity. If you are unaware about the term eccentricity, you will learn in the conic section chapter in maths. When you refer to conic section, when you study about ellipse, you'll understand about its eccentricity. Sun is lying at the one of the focus, its coordinate will be minus AE, 0. I can give you the coordinates, and that the same thing also we will study in conic section, minus AE, 0, and here the another focus will be AE, 0. This is where the focus will lie for an ellipse. Now let's refer to, I gave you all the names. Now see, this much length A, this is length A, this is length A. This is known as semi-major axis. This is length B, this is length B, this is known as semi-minor axis. Third law, the third law is law of periods, and again it's very simple. Third law of period, I'm writing here only. In this we have, the law is very simple. We have the third law, the square of the time period of revolution around the sun is proportional to cube of the semi-major axis of the elliptical orbit. So third law says that square of time period I'm talking about the entire time taken to revolve all around the sun, square of time period of planet's revolution is directly proportional to square. I'm rubbing this part. This already I believe that you must have written down. E is the eccentricity of the ellipse is directly proportional to cube of semi-major axis. When I say semi-major axis, that means I'm referring to length A, semi-major axis. Hope that you are clear about the third law. It says the square of time period. Now see, square of time period is what? T square is proportional to semi-major axis, that it will be proportional to A cube. This is what as per the law states, that because semi-major axis here will be, we have taken total length of the axis as 2A, semi-major axis will be A, and this is semi-minor axis, that is B. So we are considering this as the term that I am referring here. T square is proportional to A cube. Now how to get it? We have derived all the equations treating the orbit as circular orbit, and we can idealize the situation. In case of circular orbit, what will be the case? The only change between a circle and an ellipse is this, that the radius of the circle will be equal to both the same major and same minor axis. That is, in this case, A will be equal to B, and that will be equal to radius of the circular orbit. The only difference between a circular orbit and an elliptical orbit. So if I try to prove it, we already know. We know for circular orbit, we have already derived this, we have already proved it. For circular orbit, T was given as, time period was 2 pi by under root gm and A to the power 3 by 2. This is what we have shown already, where A is the orbit of the circular path of the, actually the radius of the circular orbit. A is the radius of the circular orbit. Now if I take squaring both sides, what I'm going to get? I will be getting T square is equal to square of the other term, squaring both sides. So we'll be obtaining T square is equal to 4 pi square by gm, and A to the power 3 by 2 whole square, you will get A cube. You see here 4 pi constant, G is constant, m is the mass of sun here, don't refer it to mass of earth. We have derived it for earth and satellite system, but here the same thing can be done for taking earth at the center, taking sun at the center and earth is revolving all around the sun. A cube. So what we are referring to, what we obtain? We obtain T square is proportional to A cube. Simple, easy, efficient, and productively we reached onto the result, that is proving the third Kepler's law. Kepler's third law says that the square of time period is directly proportional to the cube of the semi-major axis, and that is what we have shown here. Simple. First is law of orbit. Every planet is revolving in an elliptical orbit. Earth, and you all must have seen the 3D diagram when Earth is revolving in the sun. In the computer graphics image that already been shown, you must have seen definitely Earth is revolving in an elliptical orbit, and the elliptical orbit looks like something like this. And the second is law, that is law of area. The line joining sun and the earth will sweep equal area in equal interval of time. Third law, again, that's quite simple. Third law says that the square of time period is proportional to semi-major cube of semi-major axis. Here we actually try to show it by treating the orbit as circular, and we reached onto this result. Now the same thing we can do. Why we have done this? Actually, it's not required, it's beyond our scope to prove the same thing for elliptical orbit. It's not required, it will not be asked in your exam, so don't worry about that. Just know this much, this will be enough for your curriculum. Next part, completing the satellite and planetary motion. We learned about time period, we learned about conservation of angular momentum. That is pretty much required. If you are ignoring the conservation of angular momentum concept, don't do that. That will be required in solving good questions in this chapter. We did that. Now let's come to some extra points of this chapter that will be required. Some extra points before ending the chapter. Let us discuss some extra points. Now we have discussed about the potential energy. What is the potential energy? How can you think of potential energy in a different way? I am going to tell you the first extra point, that is a binding energy. Now what is a binding energy? We know that two objects separated through a distance between them, the potential energy of the system is given as minus gmm by r. So if I take two objects as this, let's say we have object of mass m1 and a second object of mass m2, both have the separation r between them. The potential energy of the system is nothing but given as minus g m1 m2 by r. This is what we know, potential energy of the system. How can we refer to this term? Do you remember while I was teaching you this? I told you, if you bring this object from infinity at this position, what you are going to get? You are going to obtain work, because you need not to do work. Force of attraction is acting on this object. So due to the internal force of attraction, it will be automatically coming to the object. You need not to do some work, you will be obtaining work. The system is losing potential energy. That's why potential energy I am giving as negative. Why negative? If the initial potential energy is 0, that when the both are separated through infinity, then we have taken potential energy to be 0, and when it is brought from infinity to this point, the potential will be reduced by this much amount. That means if you want to separate this block and take it to infinity, if you want to move this block to infinity, you have to do this much amount of work so that you can restore the potential energy to 0 value of the system that was initially when both were separated at infinity. That means this is the binding energy of the system. Hence, I can write binding energy for this system as binding energy will come out to be, this will be equal to G m1 m2 by r. What do we mean? That system is stable by this much amount of energy. If you want to disrupt the stability of the system, if you want to make them separated through infinity, you have to provide this much amount of energy, magnitude by this much amount of energy, or let's say this much amount of energy to separate both through infinity. Hence, the binding energy, the energy with which they are binded, that will be this much, G m1 m2 by r. I hope that all these statements that I've used that would clarify the concept of binding energy within you. Let's go ahead and let's apply the same in understanding the next concept, that is the escape velocity. So first extra point we learned about, that the binding energy. The second is escape velocity. Escape, I understand that whenever this point comes, escape, you all think that how can we escape from learning and from school, from classes? How can we avoid, or how can we get escape? But don't think like that. Actually, escape here is used in a different way. Any object on the surface of Earth, if it wants to be relieved from the surface of Earth, with what velocity are going to project it so that it will never come back? What I mean to say, suppose this is surface of Earth. Let us say this is Earth's surface, and if I take an object and I throw it with some speed u. If I throw it with some speed u, what it will do? It will go up and then it will return back along the same straight line. This is what the path of the object will be. It will go up. I've shown a bit distance between the two straight line paths, but they will be lying along the same straight line. That is, you throw an object, I will show you here, it will come back. Now, second thing, what if I give more speed? In that case, what will happen? More height will be traversed by the object. You see here, I gave more speed, it went through more height, it came back to me. In the second case also, it will come back to me again. So if I increase the speed, and this time I have given a speed, let's say u1, it will go through more height, but again it will come back. Can you repeat the process? Go on increasing the speed, more height, more height. Can we reach to a point when giving such a speed, object never comes back? Object is free from the Earth's gravitational pull, and if it is not affected by the gravitational pull of the Earth, it's going to leave the Earth's surface. It will never return to the Earth. It will go in space, and if it comes in the gravitational field of some other planet, it will be attracted towards that planet. So what is this speed with which you are projecting so that it leaves the Earth's surface? That is the escape velocity. Now, last term that I taught you, that is the binding energy. Let's say mass of Earth is capital M and mass of this object is small m. The energy with which it will be binded with the Earth, that will be the binding energy, and that will be G, mass of Earth, mass of the object, upon radius of Earth whole square. This will be the binding energy. And if you are confused why we have used radius of Earth, you can take the potential at the surface of Earth as minus gm by r, and when you bring an object in this potential, the potential energy will be minus gmm by r. The binding energy will be just take reverse of the negative value, it will be gmm by r. R square I wrote, oh that's a mistake, change it. I'm regularly saying r and I use r square. Make a change here, gm by r. Now, if by any means you provide it this much amount of energy, it is going to be relieved from the Earth's gravitational field. What I mean to say, suppose if I give it a speed v, if body is projected with a speed v, if body is projected with some speed v, let's say if body is projected with speed v, then the kinetic energy of the body will be how much? The kinetic energy of the body will be half m v square. This is what we know. The kinetic of the body will be half m v square, and if this energy that you are going to give the body, if that energy becomes equal to the binding energy, the body is going to escape from the Earth's surface. So equating both the two, let me call this as equation number 2 and this as equation number 1. So if you provide such kinetic energy that it's equal to binding energy, in that case 1 will be equal to 2, or half m v square can be written as g m m by r, or you can refer to this, m and m will be cancelled out. This is what we can see, small m cancels out, and we can easily obtain the value of v. That will come out to be, I am writing here, the value of v comes out to be under root 2 gm by r. This is the value of the escape velocity. Simple and easy to derive. What do we mean by this? We mean that if you give an object this much amount of speed, it is going to be relieved from the Earth's gravitational field. Proceeding further ahead, V equals to, can I write the same thing in this way? Under root 2 gm by r square. I divided one more r, I multiplied one more r here, so I have to multiply r here. So what I am going to obtain, gm by r square is small g, that is the acceleration due to gravity on the Earth's surface, and r is here under root rg. Under root 2 rg will be the value of the escape velocity. This is what you are going to obtain for the value of escape velocity. At the surface of Earth, if I substitute r and g, you see here what I am going to obtain. V equals to under root 2 rg, this is what I have used here. So if I try to find out the value on the surface of Earth by substituting all the things, 2 into 6400 into 10 to power 3, because I have to write in meters the value of radius, and g 9.8. Use it, this will come out to be nearly equal to 11.2 kilometer per second. 11.2 kilometer per second. With what speed do you ride your bicycle or your bike? With what speed you do? Sometimes 40 kilometer per hour. 40 kilometer per hour, that means in 1 second how much you will be traveling. Let me say 60 kilometer per hour you travel. In 1 hour there are 3600 seconds. So in 1 second you are traveling only 60 by 3600 kilometer. I am saying 60 by 3600, that is 1 by 60 of a kilometer. Such a small value, 1 by 60 of a kilometer if you travel with 60 km per hour. Can you imagine what speed is this? 11.2 km per second. This is a very large speed. And if you project a body with this much amount of speed, it will never come to the Earth's surface back. Now this is an ideal case we have taken. Although if you release a body, if you throw a body with a speed lesser than this speed, then also it will not come back, because it will reach into the gravitational field of some other planet, and that planet will exert a force on it, and hence it will be leaving the Earth's gravitational field. This is the escape velocity for the Earth's surface. Now once again, see the formula. V equals to under root 2 gm by r. One of the problem I was talking about, if you have seen my all classes, one of the problem I was talking about, when the mass is kept the same and radius of the planet is kept on decreasing, we found that the acceleration due to gravity kept on increasing. In the same way, if we keep mass as constant, and if we decrease the radius, that means velocity will be increased. Actually, what is happening? The acceleration due to gravity is going on increasing, and to leave such a field, to leave such a gravitational field, you require more energy. So you have to project the body with more speed. You have to provide it more velocity. That means on decreasing the value of radius, the escape velocity increases. You know, in the universe, we have such places where the escape velocity is nearly equal to speed of light. And we know that from the relativity concept that Einstein has given us, theory of relativity. The maximum speed that any object can possess, that anything can possess, that is the speed of light, that is c, that is 3 into 10 to the power 8 meter per second. Now at some place in the universe, the escape velocity is even equal to 3 into 10 to the power 8 meter per second. That means if you reach such a place, you cannot come back, because you will not be having any object that can leave the field of that particular place. Hope that you are getting what a statement I am using. Okay, that means even from such places, light will also not come back. That means if I take such a place where the escape velocity is equal to velocity of light, from here even light will also not be ejected. This place you cannot see. Such places are known as black holes. So let me write down one more term. that I told you with the escape velocity, that is the black hole. Where these are such places where escape velocity is nearly equal to speed of light, where escape velocity is nearly equal to speed of light. At such places, even light will not escape. At such places, even light will not escape. Even light doesn't escape. These are the specialty of such places. Even light doesn't escape. Such places where escape velocity is nearly equal to speed of light. Simple, easy. So such places are known as black holes. In the entire universe, we have such places, but we cannot reach there. And if you accidentally reach there, you won't be able to come back from such a place. Simple and easy, and we are done with this. So we have learned about the escape velocity, we learned about the binding energy, we learned about the black holes, we learned about the Kepler's law. Let's do one more thing. Now, I was talking about the binding energy. I told you, suppose the surface of Earth, and let's say you have an object here, its mass is m, and we have this mass of Earth as capital M. Rest all variables will be used as same. This is radius. Suppose you project it with some speed u. After reaching some height, it acquires speed v, and this height attained, let's say it is h. Here, remember, if we talk both Earth and this body as system, if I talk about both Earth and body as system, so we know that since no external force acts on the system, the total energy will remain conserved. No external force is acting on the system, total energy remains conserved. As no external force acts on Earth and body as system, total energy remains conserved. That means what I can mention, you may use one more equation for two different states. If I take the initial position, this, so total mechanical energy initial will be equal to total mechanical energy final. From here, see what you are going to obtain. You are going to obtain minus g mm by minus g m into this mass divided by the radius, is the initial potential energy, plus initial kinetic energy half m u square is equal to, see here, I am going to write the next equation equating the potential energy and kinetic energy. That will come out to be, here the speed attained is v, so kinetic energy will be half mv square, and the height attained is a h. So potential will become now minus g mm divided by r plus h plus half m v square. In some cases, you may need this energy equivalence relation also to solve certain cases. This thing also you should note down, energy can be equal to minus gm by r plus half mu square is equal to minus gm by r plus h plus half mv square. Same thing we will also use for planetary motion, satellites motion that we have discussed. I told you angular momentum remains conserved, and in those cases also kinetic energy remains also conserved. If I write here, I hope that you would have taken note of this, and let me use this part of board to understand what some more extra points about this chapter. In the similar way, I talked about this object. Now suppose any planet is moving in an elliptical orbit as shown. Any planet moving in an elliptical orbit. Now let's say here its speed is v1 and here its speed is v2. So already we have learned certain terms. If this is r1, this is r2, I have told you all the angular momentum remains conserved at these two positions. So m into v1 into r1 is equal to m into v2 into r2. This is what we have learned from the law of conservation of angular momentum. Now, if I talk about kinetic energy and potential energy, since on the sun and earth system, no external force acts on the system, so kinetic energy and potential energy will remain conserved. If mass of sun is capital M, if mass of this planet is small m, then from conservation of total energy, see what I am going to write down, from conservation of energy, we will be having a relation, I am writing down here, minus g mm by this distance, that will be r1 plus half m v1 whole square is equal to minus g mm by r2 plus half m v2 whole square. This is what you will be having in the case of planet's motion or satellite motion also. So remember, you can even use this equation and this equation for finding out velocity at some other location when you know the velocity at some particular location. So this will be useful in solving. You can see m can be cancelled out, and you can simplify further. Minus gm by r1 plus half v1 whole square is equal to minus gm by r2 plus half v2 whole square. This is what you can do, and you can also simplify the same thing. I believe that simple thing you can do when the question comes, because you are going to write the entire energy equation in the question solution. One more extra point we are left with before completing the chapter, and then we will be practicing problems on this. Relation between field and potential. We know gravitational field, we know gravitational potential, gravitational field and potential. Let's try to find out the relation. I use gravitational field lines of force to show you the gravitational field. Suppose this is the gravitational field. This is gravitational field, and let's say the field value is given as g. If I take any object here, its mass is small m. The force it is going to experience along the direction of field, will be given as F. F, we all know that this is equal to m into g vector. Now, if I displace this object slightly from this position to some position by displacing it small distance dr, hope that you can clearly see that this distance is dr. Hence, what I can write, the work done by this internal gravitational force will be how much? That will be equal to F dot dr. This is what we know, work done by internal forces. Now, F dot dr I wrote, that will be given as mg dot dr. Easy. Now, work done by internal force is equal to negative of change in potential energy. So, can I write this as minus du is equal to mg dot dr? Not a problem. Now, here if I take this m here, if I write du by m, that will be equal to minus g dot dr. Not a problem. I am going mathematically correct. Du by m is equal to minus g dot dr. Change in potential energy with respect to mass, that will give you change in potential. That means dv is equal to minus g dot dr, or for a finite position change we can write v is equal to integration dv from v1 to v2, that is equal to v2 minus v1. From 1 to 2 if you go, this will be equal to v2 minus v1, that is equal to change in potential difference. This will be equal to integration of g dot dr, where r is varying from r1 to r2. Note this formula also. I believe that you have obtained what is the relation between field and potential. Potential difference is equal to negative of integration of field dot product of field and the small displacement that we have taken. What I mean to say, if you want to understand this entire thing, when we practice more problems, then I will get that, we will be obtaining that. This is equal to, I wrote that delta V is equal to minus integration of G dot dr from R1 to R2. Suppose field is constant. And this is the gravitational field. Let's say field is constant and it's given as value of G is equal to, let's say, 10 Newton per kg. This is what has been given. Now if I move from this position 1 to this position 2, and let's say this distance is 2 meters. So change in potential while moving from 1 to 2, change in potential from 1 to 2, this will come out to be V2 minus V1 is equal to minus integration of G dot dr, not a problem, from R1 to R2. G is constant, dr is also on the same line, so the value will come out to be, finally, the value that will be obtaining, that will be equal to V2 minus V1 is equal to minus G dot dr. G is constant, you can take that outside, negate dr, will get r. So this will be equal to minus G r R1 to R2, and R2 minus R1 will be nothing but 2. So I'm going to put here minus 10 into 2. So we're going to get minus 20, and the value of unit, that is joule per kg. This is what we're going to obtain, the potential difference between the 2 points. That is, this will be the value of high potential, this will be the value of low potential. So this will be the value V2 minus V1. V2 minus V1 comes out to be negative. That means V2 will be low and V1 will be high. This is what we obtain. V2 minus V1 will be actually minus 20 joule per kg in this case. Hope that you have understood the concept of field and potential, and you can easily do cases on field and potential relation. We will be solving more problems based upon all this, and you must have known about the escape velocity, the satellite's motion, the Kepler's law, all these things. Entire chapter theory part is over. We'll be discussing question in the coming subsequent classes. Till the time, do take good care of yourself and wish you all the very best. Thank you everyone.